Hello again. So we left off by saying that these three problems, this instantaneous rate of change, this tangent line, this instantaneous velocity problem, they were all really the same problem. And they all fit under this big idea called the derivative at a point, right, at some value a. And we introduced the notation for this. And so we have this notation, the prime notation, or the D notation. And we can use this derivative, we can find the derivative by using a limiting process. Let's see some examples of this. So suppose we were given the function 3x squared minus 5x. We were to use one of the limit definitions to find f prime of 2. Alright, so we could say that f prime of 2, using the first definition, that would be the limit with x approaching 2 of f of x, which is 3x squared minus 5x, minus f of 2. F of 2 is 3 times 4 is 12. 12 minus 10 is 2. Over x minus 2. Now we know that this is going to be an indeterminate form, so we're going to use some factoring. Limit x approaching 2. 3x squared minus 5x minus 2. That one's not too bad to factor. That's going to be x minus 2 times 3x plus 1 divided by x minus 2. We can remove the common factor of x minus 2, so this is the limit with x approaching 2 of 3x plus 1. And now we can directly substitute the 2, and that gives us 7. Using the alternate definition, right, using the other definition, we could say that f prime of 2 is equal to the limit with h approaching 0 of 3 times 2 plus h squared minus 5 times 2 plus h. So that's f of a plus h minus f of a. So then this would be minus 2 over h. We expand in the numerator. So let's see, the 2 plus h squared, that is, let me just go ahead and write it. We'd have 3 times 4 plus 4h plus h squared, and minus 5 times 2 plus h still, minus 2 over h, distributing. This is the limit with h approaching 0 of 12 plus 12h plus 3h squared minus 10 minus 5h minus 2 over h. We combine like terms. 12 minus 10 minus 2 goes to 0. This becomes the limit with h approaching 0 of 3h squared plus 7h over h. We factor. This becomes the limit with h approaching 0 of h by 3h plus 7 over h. We've removed the common factor of h. That's the limit with h approaching 0 of 3h plus 7. And now letting h approach 0, this also gives us 7, as expected. So f prime at 2 is equal to 7, using either definition. You might say, well, why do we need two different definitions? Well, in some situations, the first definition is easier to work with, especially if you're good at factoring. That first definition is easier. My experience tells me that factoring is actually a weakness for most of my students, and so usually most students have an easier time with the second definition because the factoring skill usually is easier later on in the process. Both are acceptable. I personally tend to use the second definition in my instruction. Alright, so let's look at another exercise. If we had the same function, now find f prime at 4. Well, I could go through the process again. I could say that f prime of 4, that would be f of x. Limit. All right, I'd have a limit with x approaching 4 of 3x squared minus 5x minus 4 over x minus 4. And I could calculate that limit. I could use the other definition and say that f prime of 4 is the limit with h approaching 0 of 4 plus h squared minus 5 times 4 plus h minus, that should have been f of 4, not 4. And the numerator, f of 4 would be 3 times 4 squared, that's 3 times 16, that's 48. 48 minus 20, that's a minus 28. Sorry about that, I missed that. Minus 28 over h, and calculate that. But if we think about this, if we're going to have to start with a function, and if we're going to maybe need to calculate the derivative at many different points, wouldn't it be nice if we could come up with a general formula for the derivative of a function and then just be able to substitute particular values? So instead of calculating these limits, I'm going to show a different approach here. Instead, can we find a general formula, a general f prime at x instead of f prime at 4, and then substitute the 4? Can we find a general f prime at x? Well, let's use the second definition, and instead of having a specific 4, let's use a general x. Let's use a variable quantity. Alright, so let's see. F prime at x. That would be the limit with h approaching 0 of f of x plus h minus f of x over h. Notice I took that definition that we had, 2 slides ago. I took this definition here that I'm going to highlight in this magenta color. All I did was I took this definition, and instead of using a, I'm just using x. Okay, I hope you can see that. Alright, so let's see. F of x plus h. That would be then the limit with h approaching 0. F of x plus h would be 3 times x plus h squared minus 5 times x plus h. F of x minus, and now f of x is just 3x squared minus 5x over h. Alright, so now let's expand this and see if something nice happens. This becomes the limit with h approaching 0. I would have, let's see, I'd have 3 times x plus h squared. That's x squared plus 2xh plus h squared. So I'd have x squared plus 2xh plus h squared. And I'm not going to distribute yet. I'm going to leave this second term alone. Alright, so then that gives us the limit with h approaching 0. Distributing. gives me 3x squared plus 6xh plus 3h squared minus 5x minus 5h. Be careful distributing negatives. Then minus 3x squared. Actually, I'm going to go ahead and distribute here. Let's distribute through the second term here. So I'd have a minus 3x squared and a plus 5x over still over h. Now let's look at and see if there's any like terms here. Let's see. I've got a 3x squared and a minus 3x squared. What happens to those terms? They add to 0. What else do I have? I have a negative 5x and a plus 5x. Those terms also add to 0. Then what's left? Notice that everything that's left, let me highlight the remaining terms here in green. Notice that the remaining terms here, 6xh, 3h squared, minus 5h. Notice that all those remaining terms have a common factor of h. Let's factor out the common factor. So then this becomes the limit with h approaching 0. Now remember, the 3x squared and the minus 3x squared have added to 0. The minus 5x and the plus 5x have added to 0. All that's left are terms with h in them, and we're now factoring out the h. h times 6x plus 3h minus 5 over h. Removing the common factor of h, this becomes the limit with h approaching 0 of 6x plus 3h minus 5. Now, letting h approach 0, the term 3h becomes 0, and we are left with 6x minus 5. So, what is this telling us? So, if the function is 3x squared minus 5x, its derivative function is 6x minus 5. Now, in the previous exercise, previous slide, we found that f prime at 2, for that same function, we found that f prime at 2 was 7. F prime of 2 is 6 times 2 minus 5, which is 7. It works. F prime at 4 is 6 times 4 minus 5 is 19. So f prime at 4, to answer what we were actually asked for, is 19. Now, I could have gotten that same result using either of these expressions at the top. Either of those expressions should give me 19 if I've written them correctly. But if I'm going to need to find the derivative of a function at several different points, maybe it's a better idea to find a general derivative function and then make substitutions on the input. And here's a process that we can use for that. Instead of using a specific a value, use a more general x value, and then let x equal a later on. And so we call this a derivative function. Given a differentiable function, f of x. Now, I haven't really talked about what differentiable means. Okay, and I'll talk briefly about that in a moment. Given a differentiable function, f of x, then its derivative function, its derivative, is given by f prime at x is equal to the limit with h approaching 0 of f of x plus h minus f of x divided by h. Notice again that this is the same. This is the same as the second definition of the derivative, where instead of using a, I'm using x. Now, what does it mean to be differentiable? Well, it's differentiable if this limit exists, right? Differentiable. So the function is differentiable for all x if this limit exists. For all x. And we'll talk about situations where this limit doesn't exist in a later topic. We'll see some specific examples of the types of situations where this limit doesn't exist. But for now, let's assume it exists, let's assume it's nice, and we can find this derivative. And let's just learn how to use it. All right, so notation, right? We have f prime of x. More generally, we can write, right? So if y is the function of x, we can use y prime as the notation. Okay? Or we can use the f prime of x notation. Or we can have dy dx. Or df dx. Or we have what's called the differential operator, d by dx of f of x, or similarly, d by dx of y. So these are all notations that mean the same thing to me. If y is a function of x, all of these notations say, find the derivative, or this is the derivative of that function. If g of x is negative 4x cubed plus 9x plus 3, use the limit definition to find g prime of x. Then find g prime of negative 3. Alright, so what I would recommend is that you pause and try this one out on your own using the definition that I showed on the previous slide. And all I'm saying is we're using the letter G instead of F, but it's the same exact concept. Okay, now would be a good time to pause. Using the definition, G prime at x would be the limit with h approaching 0 of g of x plus h minus g of x over h. There's the definition. Now we've got to go through all the work. This is the limit with h approaching 0. G of x plus h would be negative 4 times x plus h cubed. Everywhere that I see an x in the function, first I'm replacing it with an x plus h. Negative 4 times x plus h cubed plus 9 times x plus h plus 3. There's the first term. Minus g of x. I'm just copying down the function. Notice how I'm using brackets to separate the g of x plus h and the g of x all over h. Alright, now I'm going to have to expand this x plus h cube. Alright, and if you aren't familiar with that, if you don't remember from back in pre-calculus, in general, you learned about this Pascal's triangle thing, I hope, or the binomial expansion. And so you had something like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And these are the coefficients of the binomial expansion. And so, for example, the 1, 2, 1, that's associated with a plus b squared. The coefficients are 1, 2, 1. A plus b cubed, the coefficients are 1, 3, 3, 1. So then this becomes the limit with h approaching 0. Let's expand that x plus h cubed and do nothing else right now. That would be negative 4 times x cubed, 1x cubed, plus 3x squared h, plus 3x h squared, plus h cubed. I'm going to leave everything else alone. All right, now let's distribute. This is the limit with h approaching 0 of, be careful here. I often see errors with distributions, mostly sign errors. Negative 4x cubed minus 12x squared h minus 12x h squared minus 4h cubed plus 9x plus 9h plus 3 plus 4x cubed minus 9x minus 3. Be careful. The most common errors that we see with this is when we're distributing this minus sign through the second grouping. Remember that that's going to apply to all of the terms. And most often the students make errors after the first term. All right, let's look at our terms here and see if there's, don't forget to divide by h. By h. All right, let's take a look here. We have a minus 4x cubed and a plus 4x cubed. Those add to 0. That's nice. We have a plus 9x and a minus 9x. Those add to 0. We have a plus 3 and a minus 3. Those add to 0. Let's look at everything that's left. Minus 12x squared h, minus 12x h squared, minus 4h cubed, plus 9h. Notice that everything that's left has a factor of h. Let's factor out the h. Limit h approaching 0. H by negative 12x squared minus 12x h minus 4h squared plus 9 over h. I can now remove the common factor of h, and this becomes the limit with h approaching 0 of negative 12x squared minus 12xh minus 4h squared plus 9. Now, letting h actually approach 0, then f prime, I'm sorry, not f, but g prime at x, letting h approach 0, the second term goes to 0, the third term goes to 0, I'm left with negative 12 x squared plus 9. There's the derivative function. Then g prime at negative 3, g prime at negative 3, well, that would be then negative 12 times negative 3 squared plus 9. So that's negative 12 times 9 plus 9. Negative 12 times 9, that's negative 108 plus 9 is negative 99. But again, I now have a general derivative function for my original function, and now I could find the derivative at many different points if I needed to. And that's what's nice about this, is now I can find the derivative at as many different places as I wanted for that function. Now, if I was given a different function, I go through the process again, find its derivative, substitute appropriately, but maybe there's better ways, and we're going to learn about some better ways in a later topic. Let's see one more exercise. If the position in feet of an object after t seconds is given by the function s of t is 3t squared minus 9t plus 4, find the velocity function v of t. What are the units for v? All right, so the velocity function, that's the instantaneous rate of change of the position. The velocity is the derivative of the position. The velocity is the derivative of the position. So, v of t is s prime of t. Can you take it from here? If v of t is s prime of t, write that as a limit definition, calculate the limit, and express the velocity function. Now would be a good time to pause to try that out on your own. Alright, so v of t is s prime of t, and so that would be the limit with h approaching 0 of s of t plus h minus s of t over h. So that would be the limit with h approaching 0, s of t plus h. That would be 3 times t plus h squared minus 9 times t plus h plus 4 minus s of t. S of t is 3t squared minus 9t plus 4. The denominator is h. Expanding limit h approaching 0. I'm going to do all the expansion in one step here. T plus h squared. Remembering that t plus h squared is t squared plus 2th plus h squared. Distributing 3t squared plus 6th plus 3h squared minus 9t minus 9h plus 4. Distributing. Be careful here, right? Be careful distributing this negative through minus 3t squared plus 9t minus 4 over h. Let's look at the like terms. 3t squared minus 3t squared, 0. Minus 9t plus 9t, 0. Plus 4 minus 4, 0. If something like that doesn't happen, you've made an error in your expansion of the expressions. Notice again, the remaining terms all have a factor of h. Let's factor out the h. Limit h approaching 0. H times 6t plus 3h minus 9 over h. Remove the common factor of h. Limit h approaching 0, 6t plus 3h minus 9. Now we can let h approach 0, and so v of t, the velocity function, is then 6t plus 0 minus 9. The velocity function is 6t minus 9. What are the units on v? Well, the position, right? The position was in feet in an object after t seconds. So the position was in feet. The velocity, remember, is the derivative of, as the derivative of the position, it's a rate of change. And so if we sort of think of our units in the numerator, S is a position function. S of t plus h, that's a position. S of t is a position. So these units are in feet. Here, h is a change in time, seconds. And so the velocity, the units on this velocity, are in feet per second. All right, so that finishes up this topic, introducing the derivative and finding the derivative. And this is really one of the most important topics of the course, building this derivative idea. In the next unit, we're going to expand on this by saying how we can interpret the derivative, and that there's actually an easier way to find derivatives than this long limit process. Turns out that there's some nice formulas we can use to find derivatives that make this process much, much easier. But we had to start somewhere. We had to build this concept before we can then show the nice ways to do it. All right, so I'll see you then.